Hello everyone. So in this video, I want to talk about how we can kind of build a little bit of, let's say, intuition for what the graph of a polar curve should look like by just seeing how r and theta relate to each other. So in this video, you're going to be doing a little bit of mental gymnastics, and it is kind of challenging, but I do think that it is helpful for, again, building that kind of intuition. Again, the point of these polar curves is most often to to represent graphs that are non-functions, don't pass the vertical line test. So here is an example of that. And so bear with me, keep an open mind, and you might be frustrated, but try not to get frustrated. Again, remember, we're here to learn and just see some new things. Alrighty, so the graph that we are interested in today is this function right here, this graph right here. R equals 2 cosine theta, sorry. I want to get away from saying function. R is a function of theta. I will get that out of the way because for any single theta, you're only going to get one R output. So in that sense, it is a function, but the graph is not going to pass the vertical line test. So in that sense, it's not a function. But I want to first just see how r and theta relate to each other. So I'm graphing pretty much the exact same function. I'm just representing representing the radius r with y and the angle from the positive x-axis with x. Just let that sink in for a second here. So right now, we are ignoring the polarness of this graph. So we're just focusing on this right here. Let's zoom in here. Okay. So here's the graph. So this graph, y equals 2 cosine x. It's the same old cosine graph, just vertically stretched to be twice as tall. Alrighty. So what do we know about this graph? Well, I know where its x-intercepts are, and we also have kind of 4 points of importance here. I guess actually 5. So we have our kind of starting point, our y-intercept here, which is at 0, 2. We have our first x-intercept at pi over 2, 0. We have our lowest point here at pi, negative 2. Another x-intercept at 3 pi over 2, 0. And then another peak at 2 pi, 2. And of course, this repeats every 2 pi. Okay. The reason that this is broken up into colors is because we're going to get an idea of the polar graph based on this 1/4 of the graph at a time, if you will. So in this section right here, in blue, what's happening? So I'll say for thetas now, because again, the x here represents thetas. For thetas, from 0 to 2, 0 to pi over 2, we'll write it this way. I guess we could say inclusive. That doesn't really matter here. What's happening? Well, we start off at the radius starts off as big as it's ever going to get. And then what happens is it decreases, and it's always decreasing. So the radius starts off at 2. Oopsies. Sorry about that. Starts at 2. And then decreases to eventually to 0. Decreases to 0. Again, as the angle increases, as it sweeps out. Alrighty. Now, if we follow the same idea from the red one, the red chunk right here, for thetas from pi over 2 to pi, it starts off at 0. R starts at 0. Starts at 0. And it continues decreasing. Or you could think of it as increasing in the negative direction. And gets more negative, I'll say. Gets more negative. And of course, how negative? Well, to negative 2. In the green example here, That's supposed to be kind of green there. Our R starts at -2 and gets less negative or more positive, less negative, till eventually it gets to 0 again. And then the last piece, the gold piece, all right, this is orange, so the gold piece right here, actually I think it is actually orange. The orange piece here, it starts off at 0, 0, and increases to +2. We also notice that this graph is symmetric, which means that these kind of corresponding pieces should also be symmetric on the polar graph. Okay, so let's just get a handle on this, and we'll tackle this polar graph one sketch at a time, or one quadrant at a time. So this blue piece right here, this blue piece would be represented for theta starting off at 0 degrees, and going all the way up to pi/2. The red piece would go till the red angle, which is at pi. So this is why I've drawn it I've set it up like this, excuse me. Red, and then we got green, and then the orange one last. Okay, so let's start with the blue. So we know the blue one, our radius starts off at 2. So I'm going to plot that right there. And as we increase our angle, so we're sweeping out our angle again this way, we know our radius is getting shorter and shorter. So what is that actually going to look like? Well, again, I don't have the exact numbers on me because we're just trying to build a feeling for what this graph should look like. But as I go to say maybe this angle right here, which would be pi/12, our radius is going to be a little bit shorter. When I get to pi/6, even a little bit shorter still. To what would this be, pi/4? Again, a little bit shorter. Pi/3, a little bit more. Let's see, this would be between pi/3 and pi/2, which would be, I can't do maths right here. I think this would be 4, no wait. Whatever this angle is, that's not the point of this video here. A little bit shorter, and then eventually, at pi/2, our radius is actually 0. And so, based on this drawing over here, we know that our polar graph should look something like this, some weird, funky shape like that. Again, I don't know the exact shape just based on this, but I'm just building a feeling for what the shape of this graph is. Okay, so now we're looking at these angles in red. We're looking at this chunk of the graph. Okay, so now we're starting off at 0. So we'll start off right here, that little red dot right there. And then our graph is getting more and more negative. So, for example, when I start off with this angle that I could not figure out what it is, then I'm actually going to be a little bit negative, which would mean pointing in the opposite direction, going that way. Now, as I increase the angle, as I keep spinning around our theta, then we're getting more negative. So this angle is actually going to be a little bit more negative, a little bit farther out, like so. And if we were to keep going like this, then eventually I'm going to get more and more negative, like so, like so, and like so. Now eventually, my drawing is obviously not to scale here or anything, not nearly accurate, but when I eventually get to theta equals pi, then I'm back at -2. Well, so again, that'd be -2 in the pi direction, which is this way, which actually means 2 in this direction. And so that's how I ended up back there. So maybe this should be a little bit better. I'll try to draw this a little bit more like this. I don't know, this graph might look something like this. Again, just trying to help build that intuition for what this graph should look like. I know that it should meet back up to where I started because, again, they're pointing in the exact same direction and they're the same distance out. Now let's keep going here. If I go to the green section, which again is going to be right here. So again, I'm starting off facing this way. So I'm at this point now, right there. Starting off right there. And again, my angles are getting less and less negative, but still negative. So I'm starting off there. As I start off over here, I'm going to be a little less negative. Oops, sorry, a little less negative. And so on. Notice, because we know, and we know this based on what we already know about the cosine graph, this piece, I'll highlight them. These pieces are actually the exact same shape. They're just rotated around. So due to that symmetry, this green portion is going to trace exactly over that blue portion right there. And so that's why the green chunk actually does look like that. Like so. And the very last but not least, when we get to the orange, we are again starting off at now 3 pi over 2, which is down here. Starting off with an angle, with a radius of 0, excuse me. And as we swing out from 3 pi over 2 to 2 pi, we are getting more and more positive, which means reaching further and further out till eventually getting to a radius of 2. And we will trace over that red piece right there. And so the whole point, again, the point of this exercise was to simply, okay, see how how the radius and the angle just relate to each other. Again, by picturing them as just a typical XY type of graph, rectangular graph, and then using that knowledge to craft its polar picture, the actual graph that it actually is. Okay, so this graph looks like it has some kind of like closed loop shape on the right side there of our graph. Now, is it a circle? It makes you think that it's a circle, and that's where we can use our polar to rectangular toolkit to actually transform it and prove algebraically, wait, yeah, this thing actually is a circle. I won't go into depth in that in this video because we've already done it in the last video, but I do want to just take a second here and just show you a better visualization of this via Desmos. So stand by, please. Alrighty, welcome back. So what I have here is I've pulled up Desmos. So the graph here on the left side, which I've drawn, again, this is the function f of x equals 2 cosine x, and which is the graph that we know and love. And over here, we're going to see the graph of r equals 2 cosine theta right there. Alrighty, so if I open up this is that blue portion right here where we see just the first quarter of the cosine graph. And if I see this part right here, which will represent the same points, so from 0 to 2 pi, sorry, 0 to pi over 2, we're going to get the exact same piece right there. We can also see it by tracing it out. So you'll notice I'll play the red one, or sorry, I'll play the rectangular graph right here. You see how it gets traced down. And then from here, if I go 0 to pi over 2, follow that black dot, and it goes out like so. Again, as the radius decreases, we see it over here, the radius decreases as the angle increases. Well, as the angle increases, our radius decreases on the polar graph, like that. Okay, now we can see the red piece right here. It's a little hard to see here, but this portion in red here, the second piece, and we can see the second piece in red right here, and we can see the same thing happening. So if I play this from pi over 2 to, sorry, from pi, no wait, yeah, pi over 2 to pi, we play it out like so. Likewise here, I'll go to pi over 2, which is right around here, to pi, and it gets traced out like so. Again, as the angle goes from pi over 2 to pi, the radius gets more negative, it gets further out. We see the same thing here. as the angle goes from pi over 2 to pi, our radius gets further out as well. And the last two pieces, the green and the yellow, or the green and the orange, we can see the green, which overlaps the blue part again, and the orange again, which again overlaps the red portion. So I hope this helps in some way, or maybe it does make things potentially a little bit more confusing, but that is just another way to look at these polar graphs and how we can kind of use what we know about just functions in general, and the trig functions specifically, to get an idea for what these actually look like. Okay, the reason that I think this exercise is hopefully helpful is to get the equation of this. So you would never know, arguably, to do this in the first place. Well, let's just actually get there. Excuse me. So we talked about in the last video, I said I wasn't going to do it, but I guess I will. How if I want to turn this into a rectangular equation that I actually could graph, well, we said, okay, just multiply both sides by r squared equals 2r cosine theta. You have x squared equals, x squared plus y squared is equal to 2x. And then you could complete this square and get the equation of a circle. But you would never know to do this if you didn't know the graph was a circle in the first place, right? Or at least had a circular kind of shape. You see here, I didn't even need to plug any points in, and I was still able to get like, okay, this thing looks like it could be like an oval or a circle, so maybe the equation here should be turned into the equation of a circle. And that gives me some reason to actually do this, other than do it because I told you to. Okay? So again, hopefully this helps, and at least maybe open your eyes to another way to look at these funky looking graphs.